Welcome back to Topic 6, Exponential and Logarithmic Equations. Today we're going to look at the change of base law of logarithms and logarithms in context. See, we've been playing with logarithms in ways that allow us to evaluate for some very nice logarithms. Right? We can evaluate log base 2 of 16 because 16 is a power of 2. We can evaluate log base 10 of 10 million because 10 million is a power of 10. But we don't always have a case like that, both in our just straight up made up examples, but in real life where these things are actually used. So if we had to evaluate something like, I don't know, log base 3 of 7, we can't do that without a calculator with our skills. So we need a way to actually do that. Our calculators will just have regular logs and something called ln. I don't even know what that is. Maybe someone will teach us in a couple sections. But if we can't specify the base here, how can we possibly do that? That's where this change of base law comes in. This is what it says. It says if you have a log base b of a, then you can bring them both to a common base as long as you take the quotient of the logs. So it means that if we had something like log base 3 of 7, we could say that it's log 7 over log 3. And we could say it's other things too. We could say it's like log base 2 of 7 over log base 2 of 3, or we could say it's log base 20 of 7 over log base 20 of 3, because in each of these cases, they've got a common base here. The one that really helps us is that, because that common base of 10 is something that our calculators can handle. Let's look at the proof of this one, and then let's use it. So for this one, the let statement will be to let x be equal to just our straight up initial thing on the left here, which is log base b of a, which then means to us that a is equal to b to the x. As a result, here's what we want in the end. We want a statement that involves log base c of both a and b. So we need to involve log base c here. Let's just take log base c of both sides. So we can say that log base c of the left side is equal to log base c of the right side. Okay, well, by the power law of logarithms, we can take this exponent and plunk it out in front. So we've got x log b. We've got some things in here that are kind of what we want in our final result. Right, we've got log base c of a, which is supposed to be there. We've got log base c of b, which is supposed to be there. It looks like the way we want to link them is to have them as a quotient. We want log base c of a divided by log base c of b. So let's do that. I'm going to divide by log base c of b on both sides. So I can then say that x is log base c of a, oopsie daisy, over log base c of b. But we never really had an x to begin with, did we? We had actually this. X was log base b of a, so I'll replace that. And there is this proof complete. So here's how we're going to use it. We're going to be able to approximate logs. This is similar to what I showed before with log base 3 of 7. Because our calculators can only handle base 10s, or most scientific calculators can only do that anyways, and that's how we'll compute it. We'll take something like log base 7 of 86 and evaluate it by taking log 86 and dividing by log 7. And try it out right now. Make sure you can actually do that. Hopefully you get a value of this. When you get that value, it's worth noting, does this make sense? Does it not make sense? We're saying that log base 7 of 86 is 2.289 to 3 decimal places. So for this, does this value make sense? Well, 7 to the 2 is 49. 7 to the 3 is 49 times 3, so this. So 86 would have to fall somewhere in between those values. That makes sense. And it makes sense that it's closer to 2 than it is to 3. So we can use that kind of number sense to say, yeah, this computes. I can agree with this. I'll leave that there. So just straight up try these 4 on your own real quick. Make sure you can evaluate those logs and make sure that they make sense, that you can justify why the values make sense to you. In my calculator, I would be putting that this is the log of 20 divided by the log of 4. And this gets me a value of 2.161. This makes sense to me because 4 squared is equal to 16. So 20 being close to 16 should evaluate to something really close to 2. And that's what I get here. So that's all good and well. You don't actually have to show this. It might be used for some express as a single logarithm kind of things, but you don't actually have to show that. Just note that. You have to be able to evaluate it. That's the key. I'll keep that in there. In our next example, working similarly, I might just speed through these because they're all very much the same. So we've got, let me write this a little smaller, log of 90 over log of 3. Again, you don't need to show that, but you do need to be able to say that this is that value there. Next up, log base 5 of 150, which is the same thing as log, 150 over log 5, which will hopefully get you 3.113. And then for the last example, log base 2 of 100 is the same thing as log of 100 over log of 2. I've seen a lot of people see this and say, this must be 10, because 10 squared is 100. It's very easy to make simple mistakes like that. That's not how we can convert between logs and exponents. So just watch out for it. We're asking, what exponent does 2 need to turn into 100? 2 to the power of something is 100 is what we're saying here. So that's what we're getting. Just be careful about it. In any case, we should get a value here of 6.644. And that's that value. So that's that part of it. Where does this come into play in practical application? It comes into play in these kind of contexts that we'll see on the next page. So something like chemistry is a place where you can see logs used. If you've taken chem, at this point you should have heard of pH then, if you've taken chem, which is power of hydrogen. It refers to the concentration of hydrogen ions in a solution, and that tells you how acidic or how basic that solution is. And the equation for it is that the pH is equal to negative log C, where C is the concentration of the hydrogen ions in that solution in moles per liter. So that's the link between them. Some fun facts for you. pH of gastric acid is about 2. pH of orange juice is about 3.5. And this is a scale that goes up to 14, with 7 being neutral. 7 is water, pure water. So how many times as concentrated is the hydrogen in gastric acid as compared to orange juice? Which is another way of saying, asking how many times as acidic as orange juice is gastric acid. And we look at these numbers and say, all right, 2 and 3.5, they're pretty close. So it can't be that crazy. But we're actually dealing with a logarithmic scale, so that could change things. We're going to need to find the concentration of hydrogen in gastric acid, and we're going to need to find its concentration in orange juice. And if we have those, then we can compare the factor that links the two. So let's find those two things. So first thing is we need to find the concentration of, the concentration of hydrogen ions for the gastric acid. It's your stomach acid. That's what that is. So pH is negative log C. pH of gastric acid is 2. So that's the negative log of C. And then to get C, we'll isolate slowly. Remember, we have a little invisible base of 10. So we can say that C is equal to 10 to the negative 2. We can also find the concentration of hydrogen ions for the orange juice using the same formula, that the pH is negative log C. pH of OJ is 3.5. So we've got C is equal to 10 to the negative 3.5. Whatever those values are. What we're really after is, of course, the ratio. Because we're saying that gastric acid is some amount of times as acidic as orange juice, which means that we're saying that the concentration of ions, of hydrogen ions in gastric acid, is some multiple of the concentration of hydrogen ions in orange juice. So as a result, we're really just trying to say that the ratio is, the concentration of hydrogen in gastric acid being divided by the concentration of hydrogen in OJ. And you can use exponent laws to simplify that before evaluating, but for a value, you should be getting, oopsie daisy, not that, you should be getting that. And we're going 3 decimal places as is our default in preparation for like provincial, as it tends to ask. So we can say gastric acid isn't just like 1.5 more, or however you want to interpret that. What it actually is 31.623 times as acidic as orange juice. So that logarithmic scale for pH means that if you're 1 pH lower, you're actually 10 times as acidic. It's pretty neat. Chemistry is cool. It's my second favorite of the 3 core sciences. Anyways, once upon a time we did a word problem that involved a value and investment, and we used some guess and check to actually get a final value. Is how many years does it take to double this particular investment? And we tried out values and we slowly honed in on the answer. Now that we can play with log laws and we can evaluate logs, we can do this a bit more quickly, or a bit more exactly, precisely, and accurately is what I should say. When we do this, it's necessary that we take care to not be rounding things early, and it can make an expression for the final answer look a little intense. That's okay, because we're just going to be typing into the calculator at some point, but it is necessary that we keep that expression as exact as possible the whole way through. Any poops, we want this thing to triple. So it's initially $1,000. We want it to triple, so we want A to be 3,000. This tells us that our principal amount is 1,000. Your interest rate is 3.3%. Compounded quarterly, so that's 4 times per year. And now we've got all we need to solve for t, which we don't have. So plugging everything in, got 3,000 equals 1,000. 1 plus the interest rate to the nt, which is 4t. And we're going to solve for t. And we're not going to use a guess and check method. Sweet. I would encourage you to see if you can do this. It's not necessarily the easiest thing, but explore around. It's okay if you stumble around with it. See what happens. And if you really find yourself frustratingly stuck, not just stuck, but frustratingly stuck, it's really not going anywhere, then, and only then, continue this video. What am I going to do? I'm going to divide both sides by 1,000. To get rid of that business of having a multiplier in front of the brackets. At this point, I've got something equals a power. And I need to get that exponent down. I need to get this t out in front somehow instead of being an exponent so that I can actually solve for it. And the only method I have of doing that is using logarithms. I will just take a moment to simplify what's inside the brackets to make it a bit easier to work with. So 1 plus 0.033 over 4 is 1.00825, and we're taking that to the power of 4t. And yeah, we have to use logs at this point. So I'm going to take the log of both sides. I can choose whatever base I want, but knowing that I have to use the calculator eventually, I'm just going to stick with base 10. So log base 10 of 3 is log base 10 of this other side. Using the power law, you can actually skip this step and just write log of 3 is equal to 4t log of 1.00825. If we're going to isolate t and say that t is equal to something, it's going to be the side that we have, but we have to divide both sides by 4, and we have to divide both sides by this log over here. And that's how they're attached to t through multiplication, so we're just going to use some division to get rid of them. This is the exact value of t. But in a real life kind of contextual scenario, someone asks you how long is it going to take for my investment to triple, and you as their financial advisor tell them, oh, it's going to take log 3 over 4 log 1.00825 years to do so. They're going to look at you like you're ridiculous. And you might say something like, I do not trust your instincts in this scenario. And that would be sad. You want people to trust their instincts. So get a value out of it. Do be careful with brackets. Just make sure you're dividing by that entire denominator. If you need to put some brackets around here, do so. But make sure you get an answer of 33.428. And with this being a contextual problem, make sure you have a contextual answer. And that's that. Ow. There is one more kind of doozy of an example. Not crazy doozy, but like, there's the formula. This is something that has shown up on a provincial in the past. And it looks intense. It looks really intimidating. But its principle is still the same. That's not a pun on the fact that there's a principle here, but that's not even a principle in this case. It's actually standing for payments. Anyways, moving on. We're going to plug things in, and that core goal is still the same of isolate the variable, which means we're going to have to isolate the power so that we can take the log of both sides and eventually bring this exponent out in front. If we can just get this whole power isolated. I mean, I suppose in theory you could even formulaically do that right now, but I don't know, it's up to you. There's more than one way to do this. So you contribute $200 each month into an account that offers 2.5% interest, compounded monthly. And we can calculate the projected value using this formula. So if you've opened a TFSA, if you're working, honestly, if you're employed right now, I would recommend getting a TFSA. If you are just kind of saving it, you don't need to use it right now, plug some money into there. Why not? And if you really want, you can start your RSP, but that's up to you. To be honest, the earlier you start your RSP savings, the better it's going to be for you in the long run. Regrets on my end, that's for sure, but I care about myself more now than I did years ago, so there's that. After how much time is this account going to be worth $20,000? So we're putting in $200 each month. After some time, it's going to be worth $20,000. And it's not just going to take like 100 months from these $200 each month times 100 to get you 20,000, because we're getting interest on it. So this thing's going to grow. It's going to build. So let's plug into the formula. We might need a bit of room. We might need to like go over here at some point. So let's start upper left. So the final value is 20,000. We're making payments of, so this is going to be 200. I'm going to lower this whole thing just a smidge, because I've got to have this fraction here. 1 plus r. r is 2.5%, which is 0.025. And n, it's compounding monthly, which is 12 times per year. So there's my numerator, and r over n at the bottom is 0.025 over 12. Whew! Okay. I'm going to do some things. I'm going to divide both sides by 200. I'm also going to multiply both sides by this denominator over here, just because, like, why am I dealing with complex fractions? That seems like it's unnecessary. I actually have this written out as a decimal in my own notes, but now I'm wondering, ow, what would this be as a fraction to keep things? So 20,000, we're going to divide by 200, we're going to multiply by 0.025, and so that gives me 2.5, so this side will be like 2.5 over 12, but as a fraction, we're looking at 5 over 24. So that's what that left side is. Whoopsie daisy. Yeah. You can get that with a scientific calculator. If you're struggling to get that as a fraction, just let me know and I can help you out with just how to use the calculator. I don't mean that to sound condescending, like having calculator familiarity and knowing how to use it efficiently and well is not something that everyone knows, so I want you to make sure you can use it well. Anyways, what that leaves me with on this side, will just be this business up here. So I've got 1 plus 0.0025 over 12 to the 12t minus 1. Oakley dokley's, I'm going to add 1 to both sides, which is, I don't want to do it there, which is 24 over 24. So 29 over 24 on the left side, and on the right side we've got 1 plus 0.0. I have too many zeros in my above one. Sorry about that, everyone. So 0.025 over 12 to the 12t. And this is a huge point for us because we have on this side a straight up power. There's nothing else on that side. Like, yeah, our base is really funky, but it is still a power. There's no like anything tagged along at the end. We're not multiplying by anything in front here. It's just base and exponent. And because it's just base and exponent, we can apply a logarithm to both sides of this thing. And I'm going to use log base 10. What am I doing with my font choices? And that's going to be equal to the log of this side, which means that like we're using it to drop this exponent in front. So that's what I'm going to do. I'm going to drop the exponent in front because I've applied a log to what remains. You'll notice that I haven't evaluated this part at all. I haven't simplified that to make it just 1.0 whatever that is. And that's only because 0.025 over 12 doesn't evaluate nicely. Right? It's going to be a repeating decimal. So just in the interest of avoiding that, I've still kept it in this less simplified form. It's not as nice to look at, but it's a little necessary. I'm going to continue this work over here. At this point, we're actually ready to isolate t because it's just being multiplied by 12 and multiplied by this log. And it's going to look, intense. So we're going to take this side, we're going to divide it by 12, and we're going to divide it by this log here. And that's how we'll isolate t. What does that look like? Now that I've described it, we've got the log of 29/24. I don't really need brackets there. And we're dividing it by 12, and we're dividing it by the log of 1 plus 0.025 over 12. What a formula. Like, that's intense. And you're going to have to be super careful when you plug this into your calculator. Right? Brackets everywhere. Make sure you have brackets around this whole entire denominator. Make sure there's brackets around this argument for the log. Make sure there's brackets around here, and that you actually close that bracket after. Because if those are missing, it's very easy to have this thing go down south real easily. The first time I punched this into my calculator in preparation for this lesson, I got something like -62 or something, which was obviously a wrong answer, but then I had that frustration of wondering, where did I actually screw up in entering this thing? And I'm lucky that I got an answer that was very obviously incorrect, otherwise I might not have known. What you should be getting here is about 7.578 years. And because you're doing monthly payments, it might be good to express this in months, which is going to be 91 months. Note I'm going whole number on the number of months here, because when you talk about the value of investments, you're not talking about, what's going to be after 0.056 of a month. No, these things happen at regular intervals. It might be the first of every month that the interest is calculated, and maybe you're doing your payments on the 1st and 15th of the month or something like that. But 91 months is what we're getting here. So, we can state finally, it will be worth $20,000 after 91 months. You can try what happens with 90 months if you want, because 7.758 years is like 90 point something number of months. But after 90 months, it won't be enough. It will be just a little shy of 20,000. 91 months will take you there. Now, over that much time, how much will you have contributed through your payments? For this, we're dealing with 91 months, and we're dealing with paying $200 per month. So it's really just straight up 91 times 200, which is this value. So you'll have contributed $18,200. So how much of that $20,000 is earned through interest? Well, you have $20,000. $18,200 was done by you, so the rest was interest, which is that many. Interest was $1,800, which might not seem like a lot, but over time, like if you start investing, say when you're 20, then over 35 years instead of just 7, that interest amount is going to exponentially explode. So apparently that doorbell means this lesson's over. So there's some practice work at the bottom here. Give it a try, give it a go, see what happens. If you have questions, comments, concerns, let me know, and I will see you in the future. Goodbye.